heads ringing. Keep the heads ringing.
Okay, after our lecture where we've now talked about how to place groups onto an aromatic ring by substitution, we have a relatively limited amount of them that we can get to. We basically can easily put in place a halogen, a nitro group, a sulfonate group, and an acyl group. And in rare exceptions, we can use the alkylation, but not often. It's better to bet against it. What we need to be able to do is take those relatively limited set of functional groups and turn them into others that we want, in case those don't cut it. The process is called functional group interconversion, and it's the second part of the aromatic picture. Taking those base reactions and being able to transform them into certain other functional groups attached directly to the ring. The first one is an oxidation process, and this one is particularly useful for creating benzoic acids or carboxylic acid attached directly to the ring. Now that comes in to be very useful in a number of biological or medical applications, so it's one that we need to be able to get at. The conditions here require us to have a single hydrogen on the carbon adjacent to the ring. We call that position benzylic. If we treat that with potassium permanganate, an extremely strong oxidizing agent, we're talking very unpleasant to handle stuff, it will actually tear off not only that hydrogen but also the other alkyl groups, which I have denoted here as R, and replace them all with bonds to oxygens. So we end up with, where there were 3 other attachments, we end up with now 3 bonds to oxygens, 2 separate oxygens in the carboxylic acid. This actually works on benzylic hydrogens, but as we can see from the next example, it also works if we had an alcohol present. Essentially what's happening is the potassium permanganate is forming 1, 2, and then 3 bonds to oxygen. So if we start anywhere along that trail, in the case of this next example with a single bond to oxygen and alcohol that's benzylic, it also will manage the same trick. It'll convert to benzoic acid. And if we started with a ketone, which we would get to from the Friedel-Crafts acylation, that works as well because it already has 2 bonds to an oxygen. It just needs 1 more with the loss of the alkyl group. So we can take any functionality we want as long as we have some hydrogen or oxygen attached to that benzoic carbon and convert it to a carboxylic acid. And we'll talk about why it might be useful in some of the examples later on in the lecture. But what if we wanted to go the other direction? We can do oxidation. Can we do anything functional as a reduction? And the answer is yes. There's a complementary reduction to that oxidation, that we can actually treat a benzylic ketone with hydrogen and palladium, and there's a couple other ways to do it. But what we'll get is what's called a deoxygenation, or a benzylic reduction, and we lose the carbonyl entirely, replace it with 2 new bonds to hydrogen. And as before, what we saw was that if we had other functional groups along the pathway to the carboxylic acid, we could convert those as well. The same thing is true here. If I started with a benzylic alcohol, where I've already lost one of the bonds to the oxygen, replaced either with a hydrogen or with another alkyl group, I can take that down with hydrogen and palladium as well to the alkane. And this will actually work even if I have 2 alkyl groups. It will also work if I only have 1. But the idea, though, is that it allows us now to go up and down in oxidation state relatively fluidly, because these are conditions that don't interfere with the ring, but will do reactions adjacent to the ring. And they're taking advantage of the fact that the ring helps to stabilize some intermediates. And we're going to talk about that a little bit more once we get into the ketone chapter. But what happens at that benzylic site is actually relatively special. It's not normal for most ketones to do what you're seeing on this particular example. So we're going to see this as a special example at a benzylic site. It also works if there are other pi bonds next to it, but the benzylic is the most common application. Next on the list is we're starting with the nitro group. Now that one is particularly strong conditions to put it in place, as we talked about during our first lecture. That you're talking about sulfuric acid and nitric acid. This is pretty unsubtle reaction conditions here. We can reduce that functional group down. Nitro groups tend to be relatively strong electronically. They tend to have some rather detrimental effects, not the least of which is when you attach too many of them to the ring, we call them explosives. But they tend to cause problems in other ways, and sometimes that's not what we want. Nitrogens in natural systems typically are found as amines, where you have either an NH2 or an NR2 attached to the ring, or as amides, more commonly in the amino acid cases, proteins, where you have a carbonyl attached to the nitrogen and then something else on the other side of it. So the first step along that pathway is to get rid of the nitro, get rid of those oxygens. The easiest way to do that, replace them with the hydrogens, is to take this down with a reducing agent. This is similar to what we did with the carbonyl with hydrogen and palladium, although slightly different conditions because we're dealing with the electronics of the nitrogen instead. But we can do it. It's not bad. It's the relatively smooth conditions. Iron hydrochloric acid gives us the amine. So this one is actually called aniline. It's an aminobenzene. They have some, quite a few uses. Again, we'll talk about a little bit of them in the examples at the end of the lecture. One of the things that will happen, though, is that lone pair tends to be a little too easy to use. It tends to get in our way a little bit sometimes. And so something that we're going to talk about in a lot of detail in the alcohol chapter, chapter 17, is the concept of protecting groups, where we take a functional group and we basically cover it up temporarily, or we attach something to it to modify it temporarily. And that's what you see here. It's one that's going to come into play a little bit before the end of this lecture. We're going to basically treat this with an anhydride. This is acetic anhydride, and it's going to form an amide. Now, an amide is a carbonyl directly attached to a nitrogen. Now, we can, however, reverse that, and that's the whole point of a protecting group. It does its job, you take it back off. So we can use it to modify the electronics or to keep the nitrogen out of play a little bit, even to modify the sterics because it does have a larger size with this attached to it. And then, when we don't need it anymore, we take it off. So we're going to see that, concept come up frequently. We'll talk more about it in chapter 17, but I wanted to introduce it now because it does have some uses before we finish with this chapter. The other thing we can do with that amine is something that we haven't talked about yet, is it would be nice to be able to put an oxygen directly onto the ring. And one way we can manage that is a process called diazotization. Now, your book doesn't talk about this until chapter 24, so we're not going to go into the mechanism right at the moment, but I want you to know it's possible. Basically, we treat it with nitrous acid, which is HNO2. We can't really buy that, so we use NaNO2, sodium nitrite, and a strong acid with it to protonate it in solution to give us nitrous acid. That reacts with the other nitrogen, gives us the N2 cation, which acts as a leaving group. Now, this is not your normal SN2E2 type leaving group. This is on an aromatic ring, so we're not talking about something where we can approach that carbon easily. So this is a substitution reaction, but it's a relatively odd one. So we're going to come back to the details on that later. But what I want you to see here is that from that intermediate, that diazonium cation, with a little bit of with water and a copper salt or two, we can actually turn that into an alcohol. We can put an oxygen in place directly on the ring. We had not seen that yet at all. That was not one of the groups we could put in place directly, but it's one that comes up a lot. So we have to be able to get to it. Unfortunately, getting to it's a little bit on the indirect side, but, you do what you can do. You can't, Mother Nature doesn't always cooperate with us. So we're sort of stuck with that one. Even if it's a little longer, at least we can get there. There is another way to do it, which also is not direct, but is a little bit more commonly used, and that is to begin with a ketone and do a reaction called a Baeyer-Villiger oxidation. What that does is it inserts an oxygen between the ring and the carbonyl. So we go from a ketone on the left to an ester. And then we can actually just chop the ester off with a little bit of acid or base, and we have our alcohol attached directly to the ring. Same product as we had on the previous example. However, this one we do need to talk a little bit about the mechanism of. This one will come up, it used to be in chapter 19, I'm not sure if it still is, but if it's not, it's still something we need to see. This is largely carbonyl chemistry, but it does have some applications here, as you can see, getting an oxygen onto the ring directly. So here's how it works. We're going to use the lone pair on the carbonyl oxygen, and it's going to basically attack this peroxy acid. The example here is trifluoroperoxyacetic acid. You don't have to know that, but it's a carboxylic acid with an extra oxygen. So it's looking to get rid of it. And it does. That's what the reaction accomplishes, really, is it takes an oxygen from that one molecule and puts it somewhere else. But first we actually have to have it attached to the carbon. The way that it does that is first protonating the carbonyl group. We're going to spend a lot of time on that in chapter 19, coming up real soon. And then using that protonated oxygen as a driving force to make the carbon more accepting of an incoming nucleophile. So in this case, the trifluoroperocetate ion comes in, attacks the carbon, and breaks the pi bond of the carbon to oxygen. This is something that happens literally in almost every reaction in chapter 19, 20, and 21. Nucleophile attacks, breaks carbonyl pi bond. You will get sick and tired of hearing me say that. But the reason I'm introducing it now is because it has use now. What happens next, as you can see, is a little complicated. For starters, we have something that has to take back a hydrogen. That's the beginning of a cascade. There's a lot of arrows here. That's the beginning of a cascade that involves a rearrangement. Now, that word in itself tends to be a little bit, shall we say, poorly discussed in an introductory organic book because they don't want to go into rearrangements. Rearrangements tend to cause students to have migraines and things like that. They're ugly, and you can see it from the diagram here. There's a lot going on in one single step, and there's no real way to simplify it. It's like dominoes. You know, once it starts, it has to go all the way to the end. So we have four separate electron movements here. One pulling off the hydrogen, the next reforming a carbonyl, the next, because the carbonyl is reforming, something's got to give on that tertiary carbon. What's got to give, or what actually does give, is the carbon-to-carbon bond between what was the carbonyl carbon and the aromatic ring. The aromatic ring moves down and attaches itself to the next oxygen. The process is called a migration. And, you know, we used to teach a concept about this called migratory aptitude. But the idea here is that as long as you have a simple ketone, like, you know, the R group in this case would be something like a methyl group, this will work, and it doesn't get in our way. And then that displaces the leftover ion, leaving us with an ester. Basically, all we've done is slap an oxygen in between the carbonyl and the aromatic ring. And this reaction, believe it or not, actually works relatively well. So it's a little bit simpler than the nitration. It's also a little bit milder than the nitration. I mean, as we said in class, the first lecture, nitration with nitric acid and sulfuric acid, you know, you're talking about conditions that will take most functional groups, chew them up, and spit them out in little bitty pieces. You'll be lucky if you can actually chisel your product out of the flask when it's over. So we don't want to mess with that. We'd like to have that kind of conditions out of our life as much as possible. Peroxides are not entirely that much better, but at least if you do it right, you can control them a little bit. The nitration conditions, doing it right, you know, is sort of like, okay, anything sensitive has to go in after that. There's no real flexibility in when you do things because those conditions are so brutally harsh. All right, and we'll talk about how to remove that ester a little bit later, but essentially it's a simple process. I didn't want to go into that yet. That's more of a chapter 19, 20, 21 issue, but it is very easy to do. So it's not that that's a harsh step that would really put us in trouble. We just need basically like, you know, a little time and some, you know, dilute HCl or dilute sodium hydroxide and a little bit of heat. And the last of our functional group interconversions we're going to talk about for the moment is one that happens with the sulfonate. Now we put that in place with sulfur trioxide and sulfuric acid together. Again, not exactly the world's most friendly conditions, but we can reverse that. If we take basically acidic solution, just, you know, hydrated acid, which is an aqueous acid, we can reverse that. Now, at this point, you should be saying, well, why the hell would I want to do that? I just went all this work to put it there. The idea is we're going to use that group to either block a spot or influence where the next incoming group will go, and then we don't need it anymore. Sort of like scaffolding. If you're having work done on a house, you use scaffolding to reach the siding. When you're done doing the work, you don't need the scaffold anymore. You take it down and ship it off. So that's the idea. This is a group that actually is going to be used to block and or direct things and then get lost, because like the nitro group, it has some relatively harsh effects if it's left there. How this works is essentially the reversal of what we put the sulfur trioxide group in place with, the sulfonate group in place with. We're going to have protonation first of the ring. That leads us back to the same cation we had when we made the sulfonate. But because we have a lot more water around, In this case, it's an aqueous solution instead of concentrated sulfuric acid, which has very little water. We're going to be able to deprotonate the sulfonic acid proton, and that will set off a cascade and give us back the sulfur trioxide. Now that's going to work really well because sulfur trioxide is a gas at room temperature, so in all likelihood it's just going to bubble out of the reaction, and therefore if it's not there, it can't reverse the reaction again. So that's part of why this works, is that one of your byproducts is a gas that's easily removed from the reaction mixture. Again, this is about putting something in place, the sulfonic acid group, that we can use to interfere with other reactions and then get rid of it. So that's something we're going to do a lot coming up real soon.
You need to damn read.